This is part 2 of the accumulation function, the integral video. In part 1, shown here, we established how this integral, which is this special S symbol here, between a and x, represents the total accumulation of change between a and x. This dy dt variable is the first derivative of this function drawn here, f of t. The rate of change times the small change in the input dt accumulated between a and x will give me this value of the function at x. Let's take this a step further now. So, first thing we want to do is rewrite our final equation. This time we're going to use the fact that f and y are synonymous. We're going to rewrite that integral so that we use f prime instead of dy dt. And f prime at t will give me the rate of change and allow me to do my accumulation function again. We're going to be able to add up all the small changes in f between a and x. Now looking at it this way, and in your notes, you should write f prime of t is equivalent to dy dt. Looking at this expression written in this way, we should see something interesting if we take the derivative of both sides. Remember the property of equality. If I do the same operation on both sides of an equation, I should still keep the equality. Let's do the first derivative with respect to x of f of x, and then on the right side rather, the same thing. Now you may be a bit concerned about taking a derivative with a strange operation like the integral that is very new to you. You don't have any rules for how to do that derivative. Well, we're going to see how this becomes so simple in a moment. Do not faint with fear. Now let's look at the left side first. Remember that x is a different variable than t, but it's still a variable. It's something that I can change, and therefore the function's value will change. The function f here will change depending on what x I choose. So I can find the rate of change of this f with respect to the variable x. That's simply the first derivative of f evaluated at x. Okay, the first derivative of f. Now, on the right side, what is the first derivative of a sum? Well, you just take the derivatives of each term and then you add those together. So I'm going to take the derivative of f at a, and then I'll take the derivative of this monster here. Well, how does f evaluated at a change with x? Now, don't overthink this. F here is evaluated at a fixed point A that we chose in advance. It doesn't depend on x. It only depends on A, and I'm only asking you how f changes with x. So the answer to this is simple. It's 0. The function evaluated at A acts like a constant if you're looking at x motion, the variation of x. F of A just stays still. So this is 0. I'll just leave it blank we don't need to write our 0 and clutter our board. So now the derivative, the only thing left is the derivative of this strange animal. And I want to write it carefully. The details here do matter. Now, are you trembling yet? Are you intimidated? Are you confused? Why? The answer is obvious right in front of us. See this f prime here? It is the same f that is being referred to inside the integral. And so we already have the definition of the rule called f. All we have to do is change the variable that was t here to x. Remember, one of the fundamental concepts of calculus and pre-calculus and algebra is that a function represents a set of operations, like 3x plus 9. You take x, which is the input, and you multiply by 3, and then you add 9. It doesn't matter if I call that 3u plus 9 or 3 zeta plus 9. The function's rule is defined. So if I simply write a different value, a different letter or symbol for the input, I simply have to change this part of the expression here, this part of the definition, to represent what my input is being called. So once I have defined f prime, it's the same f prime everywhere that it shows up. This is glorious because now I know the answer to this monster. I know that it's simply taking whatever this f is inside here and replacing the t with an x. This was such a big deal to mathematicians that they called it the Fundamental Theorem of Calculus. Notice that I am using the derivative to get back out the argument of the integral. When you see two functions or two operations that do that to one another, they end up undoing the work of the last operation. That's called an inverse. This is showing that the derivative is the inverse of the integral. It's so exciting in itself, but guess what? There's more. There is more. Let's go back to the original equation and rewrite it slightly. Now I'm going to isolate that integral. So I'm going to subtract f of a from both sides. And what I get is this expression. Now, this may not be impressive to you yet, but I want you to think of a scenario now where you don't know what the f is initially. All you have is the integral. So let's look at it. Let's imagine the integral's input, f prime of t. Let's imagine that we see 2t minus 3 in there. So I have this expression. From a to some point x, we have an accumulation function, 2t minus 3 times dt. Now, you know that this is an infinite series of addition problems, right? This is a limit that takes dt to 0, the little change in the input t, and I would need a calculator, amazing processing power to do this accurately. Or do I? I already know that this is the first derivative of some function f. I have enough calculus to tell you what that function f had to be. Oh, well, at least within a constant. So f has to be, f of t has to be 2t squared over 2. Remember, we're doing the antiderivative here. So that's t squared minus 3t plus any constant I want. If you go back to the derivative, just take the derivative of this, you see we do come back to 2t minus 3. All right, so all I have to do is figure out f at x. That means you plug in x to this expression. And then f at a means plug in a into this expression. And voila, you have the answer to this infinite series of accumulations. It couldn't be simpler. You could have spent hours and days coming up with a program that does this for you. But here, you spent about 5 minutes doing an antiderivative. Oh, but what about the c? Isn't that an unknown? Well, f of x would be x squared minus 3x plus that c, whatever c we choose, and f of a, do you see it yet? Would be a squared minus 3a plus whatever c we chose. Remember, if we're choosing a c, then it's going to be the same. It's going to be one c that we choose. Any c is fine, but we're still going to have the same c in the x and the a evaluations. Subtract, and what goes away? The c's. And so it doesn't matter what c you pick. In fact, you might as well just let c be 0, since it's going to go away anyway. And so there you have it. This is part 2 of the Fundamental Theorem of Calculus. And it is thrilling to see how our analytical algebra and limits can make very tedious problems as simple as this. Thank you for listening.